Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good night, everyone. Okay, in this session, we will continue trust analysis using stiffness method. Okay, let's start now. Okay, recall back to what we have learned yesterday in part 1. So the learning outcome for the trust analysis using stiffness method. Okay, at the end of this topic, you should be able to identify unconstrained and constrained degree of freedom for trust. Okay, so yesterday I have discussed how we identify degree of freedom. So what is degree of freedom and how we determine number of constrained degree of freedom and unconstrained degree of freedom. Okay, so we will continue to learning outcome number 2 for this session. Okay, so using stiffness method, we are going to calculate displacement and forces. Unknown displacement and unknown forces. Unknown forces, we divide into two. Unknown forces is unknown reaction, means reaction at the support, and another one is member forces. Okay, but before that, using stiffness method, we should start with identifying the element stiffness matrix K and structure stiffness matrix K. Okay, element stiffness matrix, the symbol we use is small letter of K because in one structure there are many elements. As I mentioned yesterday, so to have structure, the truss, for example, it is actually combination of many elements. Combination of many elements means that we will have K1, we will have K2, we will have K3 and so on depending on the question given. And K1, K2, K3 for the element stiffness matrices, okay, we use the small letter of K. And combination of many elements, we will produce what we call as structure stiffness matrix. Structure stiffness matrix, and the symbol is capital K. The symbol is capital K. Okay, and stiffness method is actually the theory behind software, the theory behind structural engineering software. So we will have to refer to the coordinate system. There are two types of coordinate system, local coordinate system and global coordinate system. So we are referring to the global coordinate system only. Okay, so after we determine or establish the element stiffness matrices, then we combine to have the structure stiffness matrix. Okay, we have to continue to write what we call as stiffness equation. Stiffness equation, Q is equal to KD. Q is equal to KD. So this Q is equal to KD is also known as force displacement equation. Okay, yesterday after I explained about degree of freedom, I also explained how we read the Q, the nodal forces at each DOF, at each node, and also the displacement D and Q at each node, and we write in matrix form. So after we establish K, we will combine Q in matrix form, K in matrix form, and D in matrix form. So we will write in one equation. So it is called a stiffness equation. Stiffness equation, we write in matrix form. The size of the matrix will be depending on number of degree of freedom. Remember degree of freedom in X and Y. For truss structure, we have degree of freedom. There are two degree of freedom in X and Y component. Okay, there are two per node. So if the truss has 3 nodes, it means that there are 6 degree of freedom. So 6 degree of freedom means for the stiffness matrix K, we will have 6 by 6 matrix. Okay, so let's say if we have 5 nodes, if we have 5 nodes, so we will have 10. 5 times 2 is 10. We will have 10 by 10 matrix for the structure stiffness matrix. So we will produce Q from Q1 until Q10 and D also D1 until D10. Okay, so why the stiffness equation is very important? Because by solving the stiffness equation, we will solve the displacement. Displacement is the first output. Displacement is the first output by applying the boundary condition. Okay, means the support condition into the stiffness equation. We will solve for the unknown displacement. Basically, unknown displacement that we can solve manually is up to 3 degree of freedom in unconstrained system. Okay, same like what we did in flexibility method, because in flexibility method we limit the manual calculation up to 3 redundant, because 3 redundant can be solved using calculator, using manual calculation as well. So for stiffness method, in order to solve to be able to solve using calculator, or in order to be able to solve the unknown displacement manually, so we limit degree of freedom in unconstrained system. In unconstrained system, up to 3 means D1, D2, D3 only. So normally, for you to solve the degree of freedom for unconstrained system, it's either 2 DOF or 3 DOF. In unconstrained system, D1, D2 or D1, D2, D3, 2 or 3 that can, so for the 2 and 3 unknown, we can solve using simultaneous equation. Simultaneous equation, however, we write in matrix form. So D, unknown displacement, is the first output by solving the stiffness equation, and after that we will use the displacement that we get D1, D2 and D3. Okay, we put back into the stiffness equation and we will solve for the unknown reaction, and also we can use the unknown displacement to solve the member forces in the truss. Okay. Okay, let's look at the fundamental of stiffness method. Okay, number one. So stiffness method, if the flexibility method is also known as force method, because redundant is force, redundant is the output, the first output. In stiffness method, we also call this method as displacement method. Stiffness method is displacement method. Because displacement is the first output. Flexibility method is force method, because redundant is the first output and redundant is force. Okay, stiffness method is also called as displacement method, because displacement is the first output. Remember, we will solve for the displacement by solving stiffness equation or force displacement equation. Okay, in truss analysis, using infrastructure, using stiffness method, we can analyze both statically determinate and indeterminate structure, and this is one of advantages of using stiffness method. Okay, next one is we get displacement and forces directly. We get all displacement and all forces directly. Okay, and this method, okay, is easy to use because it is actually the theory behind structural engineering software. Okay, so let's look at this diagram. Okay, okay, this is the truss. This is the truss. Remember, yesterday I have discussed with you, in the truss we have to make sure that there are note number that we write in, okay, number that we write in circle. Okay, we do not call note in ABC form. Okay, that is for join, conventional way. Okay, but in stiffness method, we replace join as note. It is the same thing. Join and note is the same thing, but we call as note. And note, we normally put the number referring to notes. Okay, so looking at this diagram, there are 4 notes. Note number 1, note number 2, note number 3, and note number 4. Okay, so make sure when we have a truss question given, if the note number is given, then we have to follow that label. If it is not given, or if the given note is joint name ABC, okay, when we want to analyze, we have to replace the joint ABC as 1, 2, 3, and so on. Okay, note number, and note number we have to write in circle. Okay, number 1. Number two, okay, number 2, we have to label element number, okay. Previously, when we analyze truss using flexibility method, for example, or when you analyze determinate truss, okay, previously last semester, we normally call whenever two join, okay, two nodes join together, it is called as member AB, member BC, member CD. Okay, but for truss and for stiffness method, we replace, okay, the member with element, and element we use numbering as well. But uh, but for element, we will write the element number, okay, in box. Okay, element number in box. So looking into this diagram, okay, element number one joining note number 1 and note number 2. Element number 1. Okay, element number 2 is joining note number 2 and note number 4. Note number 2 and note number 4. Element number 3 joining note number 3 and note number 1. Element number 3. Okay, and element number 4 joining note number 2 and note number 3, and element number 5 joining note number 3 and note number 4. Okay, so first one is note number, second one is element number. Okay, third one, okay, looking into this diagram, there are 4 nodes. 4 nodes mean it is 4 times 2. 4 times 2, so total DOF, degree of freedom, equivalent to 8. Because there are 2 degree of freedom in X and Y component per node. So there are all 8 degree of freedom. Means that this one we will have 8 by 8 matrix. 8 by 8 matrix. Okay. We have to label as I explained yesterday. We in order to put numbering in under degree of freedom, we have to divide. We have to divide into unconstrained and constrained system. Okay, we will have to identify number of unknown reaction, So number of unknown reaction by looking into the support condition. There are one pin support at node number 1, and one roller support at node number 4. That means there are three unknown reaction. Three unknown reaction. Means that uh, three unknown reaction, we have remaining 5, because the total must be 8. So three unknown reaction means 5 unknown displacement. 3 unknown reaction means 5 unknown displacement. Okay, that's how we read this TRUSS. Because we will have to determine unknown displacement and unknown reaction. If unknown reaction is 3, and we know that in total there are 8 degree of freedom, means 5 belong to unknown displacement. So total is 8. Okay. Another thing here is the arrow. Okay, you can see that there are arrow that we have to put uh, parallel with member, the arrow. Okay, the arrow. And this arrow is compulsory. We have to draw the arrow. Okay, so now we have five things to do. We have to put into the diagram. Okay, we have to put arrow. And arrow we can put in any direction that we like. And the arrow is very, very important. Without arrow, we cannot determine CX, CY, and we cannot solve for the stiffness matrix K. So we have to put the arrow, which is parallel with member. Okay, so there are 5 members. So we have 5 arrows. 5 members, 5 arrows. 5 members, 5 arrows. We have to put parallel with member. Okay, compulsory. And we can put in any direction that we like. Okay, so this is how we read this TRUSS. Okay, actually we should have 5 items. Okay, there are 4 here, so there is another one. Okay, next one. Okay, identify. Okay, this is important term that you have to understand. Okay, element or member. So either you use element or member also okay actually. Okay, but most important thing is we know that member is element. Element is member. Okay, and their end point. So because element, okay, this is one element. Element means end point. This is end point. One element has two end. One end. Okay, this is another end. Okay, so this is end. Two end. Okay, this two end. So this is node and node. Okay, these two end. Okay, from the arrow we will identify near end and far end. Okay, use a number enclosed within a circle to identify node. Okay, as I mentioned just now, we have to use what we call as circle. Node number we have to write in circle. Okay, the end point. Okay, the end point is node. Okay, node and node. Okay, and using the arrow, we will identify near end and far end. near end, and far end. We identify from the arrow. Okay, we can put in any direction, doesn't matter, but by having the arrow, we can identify which node is near end, which node is far end. Okay, and how to identify near and far? Looking into the arrow, because the arrow is always moving towards far end. Moving towards far ends. Okay, I will explain you later. Okay, in the diagram. Okay. So we have to put arrow. We have to put arrow in order to identify. Which end is near, which end is far. Which end is near, which end is far. Okay. Now we move to the global and member coordinate system. Okay, global coordinate system and member coordinate system. Member is also called as local coordinate. Global coordinate and local coordinate. Okay. Okay, next is loads and displacement are vector quantities. It is necessary to establish a coordinate system in order to specify their correct sense of direction. Okay, a single global or structure coordinate system XY will be used to specify the sense of each of external forces and displacement component at node. Okay, so this is just to explain about coordinate system. So item number 5. Item number 5. Item number 5 that we should put into the diagram. Okay, the truss that I have shown to you previously, item number 5 is the coordinate. Number 1 is node number. Number 2 is element number. Number 3 is degree of freedom. Number 4 is arrow. Number 5 is coordinate. Okay, number 5 is coordinate. Kinematic indeterminacy. This is another term, and actually this is representing degree of freedom. Okay, degree of freedom. Representing degree of freedom. Okay. So yesterday I have explained about unconstrained degree of freedom, where in unconstrained degree of freedom, there are unknown displacement. Means that degree of freedom itself refers to displacement. It is displacement component. Okay, represent the unknown displacement, and it must be identified. Okay, constraint. Okay, unconstrained versus constraint. Unconstrained versus constraint. So for the constraint degree of freedom, okay, displacement are 0 because the condition is always opposite. If unconstrained means unknown displacement, constraint degree of freedom, the condition must be opposite. Opposite means unknown versus known. Unknown versus known. Known means 0 displacement. So, constraint degree of freedom refers to support. Constraint degree of freedom refers to support condition, pin or roller. At support, displacement are 0. At support, displacement are 0. And what happened at support? There are unknown reaction. Unknown reaction at the support. Okay, so that is why we have to label the unknown displacement first. D1, D2, D3. D1, D2, D3. Unknown displacement we label first. Then only we label Q. We label so the reaction we use displacement to calculate reaction. So we will label unknown displacement first, then only forces, unknown reaction. So when we label, we have to label start from unconstrained, then only constrained. Okay, start from unconstrained, then only constrained. Okay. Okay, let's move to element global stiffness matrix. Element stiffness matrix or member stiffness matrix. The symbol is K. The symbol is K. Okay, this is the formula. The formula, you don't have to remember the formula to calculate element stiffness matrix. It will be given to you. Okay, it will be given to you. K, small letter of K, refers to element stiffness matrix. Small letter of K. Okay, that is the formula. The formula is given in appendix. In appendix, okay. So that's the formula, and actually the formula is quite simple. We just need to repeat the value again and again, the formula again and again. AE over L means that stiffness, looking into the formula. Okay, inside the formula, there are A. A is cross section. Cross section area. Cross section area. Okay, we get from column size. We get from wall size. Okay, that is A. Okay, it is also called as vertical element. Vertical element. Okay, A. But this refers to truss element. Okay, E. What is E? E is modulus of elasticity. This is for the material properties. In the software, E refers to material properties because different material give us different value. Okay, that is E, material. A cross section. A cross section area. In the software, A, we use the term section properties. Section properties. And another one is length. L for each element. It means that the factor that can influence the stiffness, the stiffness of the structure. Okay, there are three. It is the cross section area A, the material E, and the length of element. Okay, so diagram in the blue box, the diagram refers to the global coordinate system. Okay, there are two nodes I and node J. I and J. I is near N, J is far N. Okay, at node I, there are 2 degree of freedom labeled as 1, 2, and J labeled as 3, 4. Okay, means that there are 4 by 4 matrix for each element. 4 by 4 matrix for each element because one element has 2 nodes. Okay, this is 2, there are 4. 4 by 4 matrix. So CX and CY, okay, we use the formula. Okay, we use the coordinate to calculate CX and CY. Okay, the location of each element is 4 by 4 symmetric matrix. Each global DOF associated with the near N and followed by far N. Sometimes some books use I and J. Some books use N and F, near, far. N and F. Okay. The use of the node number notation along the rows and column, there is N and X and Y, FX, FY. Okay, that is show the position. Okay, 1, 2, 3, 4 just now. Okay. Okay, next is the structure stiffness matrix. The structure stiffness matrix. So what is structure stiffness matrix? Structure stiffness matrix combining the member or element stiffness matrices. Okay, combining the member or element stiffness matrices. Okay, depend on the total element in the structure. We combine all and we get what we call as structure stiffness matrix. Okay, And for the structure stiffness metric, we have to label the degree of freedom, and it will be labeled in order. Okay, and remember, matrix is symmetry. So we have to understand that when we deal with matrix, so we will apply all the metric characteristic. Okay, so let's move to OneNote. Okay. So under the textbook, as I mentioned yesterday, it is topic number 14, trust analysis using stiffness method. Okay, you can read all that I have explained previously. It is actually inside the textbook about the fundamental of the stiffness method. Okay, about the concept of subdividing the structure into a series of finite discrete element. Okay, most important, we have to know that how we produce the structure stiffness matrix K. We use the symbol, the capital letter of K to represent the structure stiffness matrix, and structure stiffness matrix is actually combination of many elements, combination of K1 plus K2 plus K3. Okay, we have to understand about the element or member, and the node identification. One member or one element consists of two nodes, and this node we have to identify which is near end, which is far end. Okay, near and far end will be depending on the arrow that we put. Okay, we have to refer to the global coordinate system, Okay, okay, when we want to label degree of freedom, we have to understand about unconstrained degree of freedom and constrained degree of freedom. Constrained degree of freedom refers to support reaction, and the condition between unconstrained and constrained is always opposite, known versus unknown. Okay, and once we have established the structure stiffness metric, we will substitute into what we call as stiffness equation. Then we will solve for the unknown displacement. So we jump directly into the formula of K. Okay, formula of K referring to the global coordinate system. Okay, this is the formula. We can write as C, we can also write as lambda. Okay, so this is the symbol used in the textbook. It is lambda. Lambda and C is the same. Okay, lambda and C. So previously in the final exam appendix, we use CXCY. Okay, CXCY, but since 2 or 3 semester ago, we have actually changed the symbol used, okay, for CX and CY to lambda X lambda Y. So it is actually the same thing. Don't worry, it is the same thing. Okay. Okay, in this formula, as we can see, there are label outside the matrix. N, X, N, Y, F, X, F, Y. Okay, it refers to the degree of freedom, 2 for near, 2 for far. So 2 for near, 2 for far. So we have to actually label this according to numbering that we have later on. Okay. Okay, we will take a break about 1 or 2 minutes because I have some technical problem here. So we will, okay, please join back after 2 minutes, yeah? Please join back after 2 minutes. Okay, can we continue? Okay, we focus on the diagram. Okay, just ignore about the feet unit used here. So assume that this is 4 meter and 5 meter. Okay, we use the SI unit. Okay, so we want to analyze this truss. We are going to establish number one, element global stiffness matrices K1 and K2, K1 and K2, and number two is the structure stiffness matrix. So that is the aim for this session, the objective for this session. Okay. Okay. Now this diagram, this is a truss. This is a truss. This truss has three nodes: node number one, node number two, node number three. Node number one, node number two, and node number three. Okay, remember, in one truss diagram, in order to establish the structure stiffness matrix, before we start doing anything, okay, to apply formula, the K formula, we have to put 5 item into this diagram. Okay, number one is node number. Number one is node number. Node number is given. Node number is given. Number two is element number. Number two is element number. Okay, element number. So there are 2 elements. So we can put in any element that we like. So let's say we have like this, element number one and element number two. Element number one and element number two. Okay, the next one is degree of freedom. So when we want to label degree of freedom, normally we have to sketch. Okay, we have to sketch diagram, okay, separately. We divide into two systems. One is unconstrained, one is constrained. Unconstrained and constrained. Unconstrained and constrained. Okay, unconstrained and constrained. Okay, just sketch like this. Okay, and then refer back to the diagram. Okay, look how many how many support. Okay, looking into the diagram, there are four unknown reaction which come from 2 pin support. Four unknown reaction means 4 degree of freedom. 4 unknown reaction means 4 degree of freedom. Here, these 4. Because the total is 3 times 2. Total is 3 times 2 because there are 3 nodes. Okay, looking at the support, there are 4 unknown reactions. So directly we put 4 degree of freedom in x and y component. Okay, at the support position. Okay, so this is unconstrained. Unconstrained first, then only constrained. Okay, so 4 degree of freedom. 4 degree of freedom in constrained system, which is equivalent to 4 unknown reaction. So there are remaining 2. 2 degree of freedom. 2 degree of freedom. Okay. At node number 2. And node number 2 is not support. Okay. So from this, what can we read from this? Okay. 4 means for unknown, for unknown reaction. Unknown reaction, for unknown reaction. U for unknown reaction. And for known displacement. Known displacement. Okay, known. We use K for known. Known displacement, unknown reaction. Okay, for unconstrained system, we have two unknown displacement. Two unknown displacement, U for unknown, two unknown displacement, and two known Q, known forces. So this is how we read the information from degree of freedom between constraint and unconstrained and constraint. Okay, when we label, because the unknown displacement will be determined first. This one first. Okay, then only reaction at the support. Okay, we will determine unknown displacement, then only we can determine unknown reaction. So that is why when we label, we have to label start from unconstrained. 1, 2, 3, 4, 5, 6. Okay, so now we combine. Okay, we combine. Okay, combine. So this is the TRUSS. Okay, this is the TRUSS. Okay, the label for the TRUSS is note number 1, 2, 3. So this is 1, 2, 3. 1, 2, 3. Element 1, element 2. And then the degree of freedom. In total, there are 6. Okay, 1, 2. This is 1 and 2 at node number 2. And then 3, 4 at node number 3. And 5, 6 at node number 1. Okay. We can also put 3, 4 at node number 1. Doesn't matter. Alright. This is how we label degree of freedom. We have to label according to unconstrained and constrained system. We label unconstrained first. So total must be 8. So this 8 degree of freedom actually representing position. There are 6 position. Okay. Next is arrow. We have to put arrow. Okay. In any direction that we like. You can also put like this if you want. Okay. Doesn't matter. You can put in any direction. Okay. Arrow is compulsory because we have to, when we calculate Cx, Cy, or lambda x, lambda y, we have to calculate we have to calculate from the arrow. Okay, because from the arrow we identify near end and far end. Okay. And lastly, item number 5 is coordinate. So we have to put coordinate. Normally we will choose one as origin, one node as origin, and we will label the others based on the origin that we have chosen. Okay, so previously it is 3 and 4. 3 and 4. Okay, looking into the diagram, so I change the distance, yeah. Okay, this is, let's say this is 12, this is 5 meter. Okay, I change the distance. Okay, 5 and 12. 5 and 12. Okay, now from this, can we put the coordinate when we have origin? When we have origin, yes, we can put the coordinate. Okay, coordinate x and y from the origin that we have chosen. Okay, normally when we want to choose origin, we make sure that we will get all positive coordinate. For example, if we choose 1 as origin, we will get negative coordinate for 3 and 2 and 3. Okay, you get what I mean? If we choose 3 as origin, we will have negative coordinate at node number 2. But when we choose 2 as origin, so all 1 and 3, we get positive coordinate. It is just a tip. Okay? So now we choose 2 as origin. Okay? So at origin, it is 0, 0. So from this, we will label the coordinate node number at node number 3. At node number 3, so we will get 12, 0. 12, 0. Okay. And for node number 1, okay, the coordinate is okay, for node number 1, the coordinate is, okay, you can write the answer in the chat box. Okay, coordinate number 3 is 12, 0. Coordinate number 3 is 12, 0. We refer to the origin at node number 2. What is coordinate at node number 1? What is origin? What is coordinate at node number 1? Okay, it is 12, 5, right? Okay, it is 12, 5. Yeah, it is 12, 5. Okay. So these are all 5 items that we have to put before we start doing the step after this. Means that we have to analyze, determine, or the special word is establish element stiffness matrix. We cannot establish element stiffness matrix without having all this inside the diagram. We cannot establish element stiffness matrix without having all this information in the diagram. Okay? Okay, now we will move to the first step. We will calculate, we will establish what we call as element stiffness matrix. Element stiffness matrix. Okay. Okay, it is okay. It is called as element stiffness matrices. That is the name. Matrices for plural. Because for element, there are more than one, right? That is why it is matrices. Okay? Element stiffness matrices. And we will establish one by one element. Means that we have to focus one by one element. Okay? We focus one by one element. Okay, focus on element 1 first. For element number 1. Okay, we focus on element number 1 first. Okay, element number 1. Okay, this is for the first exercise. This is for the first exercise. Okay, what I want to suggest to you is as the first exercise, right? So start with extract all information from element 1. Okay, in other diagram, just to draw the element 1 diagram. Okay, in element 1, this is the arrow. Okay, node number 2 and node number 3. Okay, from the arrow, we know that 2 is near, far is 3. Okay, from the arrow. Okay, what is inside this? Okay, this is element number 1. Okay, 0 0, the coordinate, this one is 0 0. Okay, this one is 12 0. Okay, element 1, the length is 12 meter. Okay, what else? The degree of freedom, right? Degree of freedom. Okay, for node number 3, degree of freedom is 3 and 4. And for node number 2, degree of freedom is 1 and 2. Okay. Okay, there are node number, element number, degree of freedom. Okay, there are 4 degree of freedom. Okay, 2 each nodes. Okay, XY, 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 XY. And then arrow, don't forget to put the arrow because we identify near and far end from the arrow. And lastly is the coordinate. Okay, clear? Okay, now from this we have to calculate lambda x, lambda y, or Cx and Cy. Lambda x, lambda y, or Cx and Cy. So I choose to use Cx, Cy instead of lambda x, lambda y. Okay, because it is easy to write, right? Okay, Cx and Cy. Cx and Cy. Okay, why we have to calculate Cx and Cy? Because inside the formula, we have to calculate that. Okay, let me show you the appendix that have been used so long. Okay, but now I have to follow what is used in the textbook, lambda x, lambda y. So in your final exam, you will find that the symbol used is lambda x, lambda y. Anyway, you can also write Cx and Cy, doesn't matter. Okay, so this is the formula that we are going to use, Cx and Cy. Okay, there are several things that I want to highlight here. Number 1, it is 4 by 4 matrix for one element because of 2 nodes, 4 by 4 matrix. Okay, 4 by 4. Another thing is the matrix is symmetry matrix. Symmetry. Okay, symmetry means like this. Okay, symmetry. Okay, you understand, right? What is symmetry, right? Okay, symmetry matrix. Okay, next is you can find that this value, this 4 value, is actually same with this value. Same formula. And the other, this 4, same with this. Okay, and between the blue and the green, the difference is only due to the sign, positive and negative. That is so simple, straightforward formula, and you don't have to remember. Okay, AE over L is 4 by 4 matrix, and there are 4 by 4. So this is the boundary between near and far. the boundary between near and far. And remember, near we have xy. Near we have xy, far we have xy. Okay, near we have xy, far we have xy. Okay, so we will refer to this formula. Okay, we refer to this formula. Okay. So now we want to calculate Cx and Cy because when we want to establish element stiffness matrices, okay, we have to have Cx and Cy. That's all. Okay, how to calculate Cx and Cy? You don't have to remember the formula. Just focus on, okay, just focus like this. Cx means look at x value. Cy, look at y value. We have coordinate x, coordinate y, right? Coordinate x and coordinate y. Okay, at node number 2, we have x and y. At node number 3, we have x and y. So, when we want to calculate Cx value, just focus on the x value. X value. So, looking into this diagram, the x value, okay, we have near x, we have far x. Okay, near x is 0, far x is 12. Near x, this is near x. Okay, far x is 12. So Cx is 12, far minus near. Divide by length. Length is 12. Divide by length. Length is 12. So this one is equal to 1. This is equal to 1. Okay. Now, when we want to calculate the value of Cy, we have to refer to y value. Okay, this is y for near, y for far. It is far minus near. Far minus near. So, this one is 0 minus 0 divided by length 12. So, this is 0. Okay, Cx, Cy. Cx, Cy for element number 1. For element number 1, we get like this. Okay? Understand, yeah? Okay, now we want to substitute into the formula. This is the formula. Remember, do not write the formula. Just put the answer. Okay, Cx square, Cx, Cy, all this value, we have to divide by L. We have to divide by L. And just keep the answer in terms of AE. We don't have to put AE value. Just give the answer in AE form. In AE form. So the first value, okay. So it is K1. It is K1. It is 4 by 4 matrix. Cx square divide by L. Cx square divide by L. What is the answer? Cx square. Cx is 1. Cx square is 1 square divide by 12. Okay, can you give me the value 1 divided by 12? Okay, 1 divided by 12. Okay, please calculate for me 1 divided by 12. What is the answer? It is cx square 1 times 1 square divided by 12. So we will produce 0.083. So this is 0. This is, don't forget to put AE here. Okay, 0.083. 0.083. Then CX, CY, because CY is 0, the next value is 0. Okay, 0. There are so many zero value whenever the member is horizontal or whenever the member is vertical. Okay, we will get all value without zero whenever the member is inclined member. Okay, and then negative CX square. Negative CX square means negative 0.083. Negative 0.083. Okay, and next one is 0. 0. Okay, next value, focus on this. CY square. CY square, because we know that, because it is symmetry, we know that this is also 0. Okay, next value is CY square. CY square over L, it is also 0. So all these are 0. Okay, then it is negative 0.083. It is 0. It is 0.083. Because remember, this 4 value, same with this 4 value, right? Okay, so the value is 0, 0, 0. Okay, like this. So this is actually K1. This is K1. Okay, this is K1. 4 by 4 matrix. 4 by 4 matrix. Okay, but this is not finished yet. This is not finished yet because we have to label the K. Okay, we have to label this based on degree of freedom. Okay, based on degree of freedom, we have to label. Okay, it is near XY, near 1, 2, far XY is 3, 4. So the label is 1, 2, 3, 4. Okay, 1, 2 first, near first, followed by far. Near, followed by far. At near, we have to put, we have to follow the order XY, near XY, far XY. Near XY, far XY. So it is 1, 2, 3, 4. So 1, 2, 3, 4, we have to label like this. 1, 2, 3, 4. Sorry. 1, 2, 3, 4. This is 1, 2, 3, 4. 1, 2, 3, 4. Okay, this is element stiffness matrix for element 1. For element 1. Okay, it is very simple. Theory. The theory, of course, you have, I explained the theory quite detailed. Okay, because the theoretical part is very important. However, for the solution, it is quite straightforward, just like this. Okay. Okay, next. Okay, next, we want to move to element number 2. So I want to extract now element number 2. Okay, so we have element number 2. Okay, element number 2, the length for element 2. What is the length for element 2? 5, 12. What is the length? What is the length for element number 2? Using trigonometry, what is the length for element number 2? Okay, using trigonometry, what is the length? We have 5, we have 12. So what is the length? What is the hypotenuse? Element number 2 is inclined member. What is the length? Okay, can somebody tell me what is the length? If 3 and 4, we have 5. If 5 and 12, we have? Okay, we have one triangular like this. It is just like one triangular like this. This is 12, this is 5. Okay, what is value of this? Okay, yes, it is 13. It is 13. So the length for element number 2 is 13. The length for element number 2 is 13. Okay, now we will produce K2. We will start with extract all the information. We will extract all the information. Okay, the arrow, note number 2, note number 1. From the arrow, we know that this is near, this is far. Okay, this is element number 2. The coordinate is 0, 0, and 12, 5. 12, 12, 5. Okay, degree of freedom, 1, 2, 1, 2, 5, 6, right? What is the label that we use? 5, 6. Yes, 5, 6. 5, 6. Okay, so from this we repeat the same process. We have to start with calculating Cx and Cy. Calculating Cx and Cy. Cx refer to x coordinate, Cy refer to y coordinate. Okay, Cx refer to x coordinate, Cy refer to y coordinate. It is far minus near. It is far minus near. It is 12 minus 0. Far minus near. 12 minus 0, we divide by L. L is 13. L is 13. It is 12 divided by 13. What is the value of Cx? What is the value of Cx? Okay, can somebody please calculate for me? 12 over 13. What is the answer? And for Cy, we have to refer to y coordinate, far minus near. It is 5 divided by 13. It is 5 minus 0 divided by 13. Okay, 5 minus 0 divided by 13. Okay, please calculate for me one Cx and another one Cy. 12 over 13 and 5 over 13. What is the answer? Okay, Cx is 0.923 and Cy is 0.385. Okay, 385. This is 3. 385. 0.923 and 0.385. Correct. Okay. That is why I said just now, when we have when element is horizontal or when element is vertical, we will get all 0 value in the matrix. But when the member is inclined member like this, we don't have 0 value in the matrix. All value, not 0. Okay, so please calculate now for K2. For K2, this is K2. In terms of AE, okay, we have to divide by L. It is Cx squared divided by L. 0.923 square divided by length 13. Okay, please calculate for me the first value. This is the first value. 0.923 squared divided by 13. What is the answer? What is the answer? 0.923 square divided by 13. It is Cx squared over L. 0.066. Okay, it is 0.066. 0.066. Okay, next value is CXCY. CXCY. If we refer to the formula, CXCY. CX square, CXCY. Okay, CXCY. CXCY 0.923 times 0.385 divide by 13. Divide by 13. 0.923 times 0.385 divide by 13. Okay, what is the value? What is the answer? What is the answer? 0.923, 0.385. Okay, divide by 13. 0.027. 0.027. So, we get 0.027. Okay, and then we get negative 0.066. And then we get negative 0.027. Okay, and then because it is symmetry, right? So 0.027. Okay, next is next value for this one. Okay, next value. CY squared. CY squared over 13. CY squared over 13. CY squared. CY. CY squared. Okay, over 13. Please calculate 0.385. 0.385 square divide by 13. 0.385 square divide by 13. 0.11. 0.011. Okay, 0.011. Okay, so negative 0.027. So just complete the matrix. Negative 0.011. Okay, next, negative 0.066. Okay, negative 0.027. Because this line, same with this line, right? Okay, because it is symmetry matrix. Symmetry matrix. Okay, next value. Okay, negative 0.027, negative 0.011. Another checking is this 4 value and this 4 value is also same. Okay, another checking. Okay, and the next 4 value will be equal to this. Okay, the next 4 value. So we have 0.066, 0.027, 0.027 and 0.011. Okay. Okay. Okay, this is K2. This is K2. And remember, what most important is degree of freedom label. Okay, we label outside the matrix, representing near XY, far XY. We have to refer to the diagram. Okay, refer to the diagram. Near XY is 1, 2. Near a far XY is 5, 6. Near XY, 1, 2. Near XY. Far XY, 5, 6. So, the label for this K2 is 1, 2, 5, 6. The label 1, 2, 5, 6. 1, 2, 5, 6. Okay. So this is the element stiffness matrices K1 and K2. K1 and K2. Okay, it is actually quite straightforward. The formula is quite simple. Okay, the formula is quite simple. To calculate Cx, Cy also straightforward. Okay, we just need to understand about the coordinate. Okay, then we just have to substitute into the formula and we get K1 and K2. And for element stiffness matrices, it is most important thing to label the degree of freedom. Okay, 1, 2, 5, 6, 1, 2, 3, 4. Previously, K1, we get 1, 2, 1, 2, 3, 4, right? 1, 2, 3, 4. And for K2, we get 1, 2, 5, 6. 1, 2, 5, 6. We have to label this correctly because it is actually representing the position in the structure stiffness matrix. The position in the structure stiffness matrix, it should be 6 by 6 matrix because of 3 times 2, 3 times 2, total is 6. Okay, looking back into the diagram, there are 6 position of degree of freedom. 6 position from 1 to 6. So this 6 mean we will produce the structure stiffness matrix and the size of the matrix is 6 by 6. Means that the label that we use, that we put, okay, in K1 and K2 representing the position in the structure stiffness matrix. In the structure stiffness matrix. Okay. So for the structure stiffness matrix, okay, structure stiffness matrix. Okay, this is K capital. This is K capital. And this K is actually equal to K1 plus K2. For this, for this question, to get the structure stiffness matrix, we get from two elements, K1 and K2. K1 and K2. And K1 and K2, we have 6 position. We have 6 position. Okay? Wait for a while. I want to get the matrix 6 by 6. Okay, for math. Okay.
Baik ni cover ni lah. Nak pakai buku semalam. Hai buku.
Wait.
Tu baik cover hilang.
Sorry, anak susun buku. So it is 6 by 6, right? 6 by 6. So this is 4, 5, 6. Okay, this is 6, 3, 4, 5. 5, 6 by 6. Okay, 6 by 6. And I want to have this for the label. 4, 5, 6. So this is 1, 2, 3, 4, 5, 6. Okay. Okay. Okay, now we are going to produce this stiffness matrix. The stiffness matrix, this is K. K in terms of EA. Okay, so in the structure stiffness matrix, we have 6 by 6. 6 by 6 because of 6 degree of freedom. 6 degree of freedom. So this is the stiffness metric for the structure. Remember the term mentioned earlier about subdividing structure into element. Asalnya a structure, the truss. Okay, subdividing structure into element because we want to produce the structure stiffness metric. We have to produce from element stiffness matrices. We cannot get directly the structure stiffness metric using one formula, cannot, because the formula to calculate stiffness metric is for each element. That is why we have to divide into element. Establish the element stiffness matrix first, then only we combine to have the structure stiffness matrix. Total is 6 by 6. Total is 6 by 6. Okay, 6 by 6 in terms of EA. So 1 to 6 means the degree of freedom, the position. The position. 1, 2, 3, 4, 5, 6. This is also 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Horizontal and vertical. The position. So the value, so we find from K1 and K2. We find from K1 and K2. Okay, means that this is 1, 1, the matrix, right? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Remember the matrix? The matrix. Okay, this is 1, 2, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. This is 6, 6. This is 5, 5, 4, 4, 3, 3, 2, 2. Okay, the matrix. All the matrix characteristic, okay, we have to apply into this. Okay, 6 by 6 matrix. Okay, now we want to calculate the value for 1, 1. The value for 1, 1. Position 1, 1. Find the value in K1 and K2. 1, 1. So 1, 1 in K2 is 0.066. That is 1, 1. And 1, 1 in K1. 1, 1 in K1 is 0.083. 0.083. Okay, please plus these two value, the same position. Position 1, 1, it is 0.083 and 0.066. Okay, Please find the value of 1, 1 in the structure stiffness matrix. 0.0, 0.066 and 0.0 and 0.083. What is the answer? 0.149. So this is 0.149. 0.149. Okay, next is position 1, 2. Position 1, 2. Position 1, 2. 1, 2. Position 1, 2. It is 0.027. 0.027. 1, 2. 1, 2 is 0.027 and 0 for K1. K1, 1, 2 is 0, right? Okay, 0. Okay, this is this is 1, 1. 1, 2, sorry. 1, 2 in K1, 0 and 1, 2 in K2 is 0.027. So the value is 0.027. Okay. Next value is 1, 3. 1, 3. 1, 3. 1, 3 is 1, 3. 1, 3. 1, 3 is negative 0.083. 1, 3 is 0.083. 0.083. 1, 3. Negative, negative. It is negative 0.083. Okay, 1, 4. 1, 4. From K1, it is 0. From K1, 1, 5. 1, 5. This is 1, 5. 1, 5. Okay. So numbering that we put in K1 and K2 refers the position in the structure stiffness matrix. 1, 5 is negative 0.066. It is negative. Negative 0.066 and negative 0.027 and negative 0.027. Okay. And actually in metric, you don't have to write the value here. Okay, because it is symmetry, right? So if you don't want to write, also okay. Okay, now the next value is 2, 2. 2, 2. 2, 2. 2, 2 we get from K2. We get from K2 and the value is 0.011. 2, 2 in K1 is 0. Okay, so it is 0.011. So here the value is 0.011. Okay, next position is 2, 3. 2, 3. Next position is 2, 3. Okay, there is no 2, 3 in K2, so move to K1. 2, 3. 2, 3. 2, 3 is 0. 2, 3 and 3, 2 is the same value. 2, 3 is 0. 0. 2, 4 also 0. Okay, 2, 3, 2, 4, 0. 2, 5. 2, 5. 2, 5. 2 and 5. Okay, it is negative 0.027. Find the value in K1 and K2. Negative 0.027 and 26 is negative 0.011. Okay, negative 0.011. Okay, so next we move to 3, 3. We move to 3, 3. So 3, 3. 3, 3 is 0.083. 33 is 0.083. Okay, 33 is 0.083. 0.083. 0.83. Okay, 33, 34, 34, 34 is 0. 35, 35. Find 35 in K1 and find 35 in K2. There is no 35 in K2 and also there is no 35 in K1. No 35 in K2, no 35 in K1. So we put 0 here. We put 0. 36 also there is no value. Okay, because we cannot find 36 in K1, we cannot find 36 in K2. So the value is 0. So next we move to this. Okay, it is 4, 4. 4, 4. Okay, 4, 4 we get from K1. There is no 4, 4 in K2. We get from K1, it is 0. It is 0. Okay, it is 0. 4, 4 is 0. 4, 4 is 0. So here, 4, 4 is 0. Okay, 4, 4 is 0. 4, 5. 4, 5. Next position is 4, 5. 4, 5. Again, 4, 5. We cannot find 4, 5 in both K1 and K2. We cannot find 4, 5 in both K1 and K2. So it is 0. 4, 6 also 0. When we cannot find the position, the position in K1 and K2, so means there is no intersection. Okay, the value is 0. Okay, next value is 5, 5. 5, 5 we can only get in K2. 5, 5 value is 0.066. 0.066. 0.066. That is 5, 5. 0.066 here. Okay, and then 5, 6 is 0.027. Okay, 5, 6 is 0.027. 0.027 and 6, 6 is 0.011. 0.011. Okay. Okay, this one I want to change color because it represents the position. So this is the structure stiffness matrix. The structure stiffness matrix. Okay. So this is also 1, 2, 3, 4, 5, 6. Okay. So when you are asked to establish the structure stiffness matrix, so that is why we have to subdivide the structure into element, because we can only calculate element stiffness matrices from the formula. Formula K come from element. Then that is why we have to divide into element. Okay, that is why the structure we have to divide into element. Okay, and from element we calculate element stiffness matrices. Okay, and we have to label the element stiffness matrices. Okay, based on the near and far and near xy far xy. Remember, near xy far xy is actually the position, the degree of freedom position in the structure stiffness matrix. And from element stiffness matrices, we combine to have the structure stiffness matrix if there are two elements, K1 and K2. So it is K1 plus K2. The size of the matrix is depending on the total degree of freedom. It is 6 because 3 times 2. So the structure stiffness matrix must be written in order. In order means 1, 2, 3, 4, 5, 6. Okay, we cannot compare with the element stiffness matrices, because for element stiffness matrices, we have to label according to near XY far XY. Okay, so from that, we produce the structure stiffness matrix. It is just a simple mathematical process. We just have to plus the value which is in the same position when there is no position, when we cannot find the position in K1 and K2, means we have to put 0. So this is the product. This is the structure stiffness matrix. This is the structure stiffness matrix. We have to establish this before we can calculate the unknown displacement and unknown reaction. Okay, this is very important step. Okay, and in order to have this, we have to understand several important terms. Okay, the unknown degree of freedom, the unconstrained degree of freedom, the constrained degree of freedom. Okay, so that we can produce the matrix, the structure stiffness matrix like this. Okay, so don't worry if you have put different arrow or different label, doesn't matter. It is just the matter of position only. Okay, so that's all. That is how we identify, we analyze, we establish the structure stiffness matrix. Okay, do you have any question? So for tomorrow's session, I will continue to finish this exercise. This example, I will finish this. Means that I will continue to apply Q is equal to KD. I will show to you how are we going to calculate the unknown displacement and unknown reaction at the support. And after that, I will continue to show to you how we can calculate the member forces in the truss. So this is for tomorrow. This is for tomorrow's session. So to complete the one truss question, okay, so we have to calculate unknown displacement, unknown reaction, and member forces. Okay, I think that's all for part number 2. We will continue part number 3 tomorrow night. Okay, tomorrow night. Okay, thank you very much. Thank you very much. Thank you for joining. So please try to do it on your own. Thank you. We meet again tomorrow. Okay. Assalamualaikum warahmatullahi wabarakatuh, and good night, everyone.